So the focus of this lesson is looking at inverse functions, which is actually a huge topic, and we're just introducing some ideas. And if I look right here, I have a function f of x, which is a linear function. The inverse of it is a function that undoes it. And there's many sort of ways of looking at this. Or the inverse function compared to this swaps around the inputs and outputs. So whatever number goes into this function comes out. Well, for the inverse, it's the other way around. Whatever goes in, everything is swapped around for this. And so first, if I want to find the equation of the inverse, the most formal way is to algebraically take this equation and swap around our inputs and outputs. By that I mean, the most standard way of showing an equation is, y is your output, x is the input. Well, let's swap those around. And so let's make x the output and y the input. Now, if I end up solving for y in this equation that I have now, I will end up having the inverse of f, the function that undoes what f does. And so let's solve for y. Pretty quick, 2 steps. I can add 5 to both sides. I get x plus 5 equals 1/2 y. Almost done. To get y by itself, I want to multiply both sides by 2. And so I want to double everything. And so I can write this either as 2 times x plus 5 equals y, or I can distribute it out. 2x plus 10 equals y. Either way, it's all the same thing. And so to write it in the formal notation we have up here, I'm going to say, therefore, that the inverse of f equals, I'll go with the first one I had, 2 times x plus 5. And the reason I'm going with this one is that it makes it a bit more explicit about how this here compares to this. Notice if you look at function f, whatever number you substitute into into x, I should say, the first thing you do is multiply by 1/2, and then you subtract 5. For my inverse here, everything is reversed, including the order. So if we look back at function f, the first thing we did was multiply by 1/2. Well, in here, the last thing we do is multiply by 2, which is the inverse of that. And over here, the last thing we did was subtract 5. Here, the first thing we do is add 5. Either way, I now want to use this inverse equation to find f at -17. Should be quite quick. The input of my inverse is -17, so I replace that x with -17. And it's a matter of just a bit of arithmetic. So equals 2 times -17 plus 5. Do the calculations and you get -24. Keep in mind, if I look at what I say here, maybe I'll write this a bit more formally here, the inverse of f at -17. For my inverse, I put in -17, I get out -24. That means I know, if I were to do this the other way around, if I put in -24 into f, I know I'm going to get out -17. I'm too lazy to actually prove it to you, but you can prove it yourself. And in general, whatever number goes into your function comes out. Well, if I do it the other way around, if I put that into my inverse, I go back to where I started. And so again, all this idea of inputs and outputs swapping around becomes a crucial idea to everything we do. So next, let's look at another simple function, g of x, which I have graphed here as well, 2x minus 4. I want the equation of the inverse, and I want to sketch it. So same idea as before. I'm going to find this algebraically. I'm going to first write g of x as y equals 2x minus 4. That's g of x. I want the inverse. I want to swap around my inputs and outputs. And so this is now going to be x equals 2y minus 4, and solve for y. Nice and quick. Add 4 to both sides. Divide both sides by 2. I get y equals x plus 4 over 2, which is also the same as x over 2 plus 2, if you break this up into 2 separate terms. And that's my inverse. So I'll write this formally, the inverse of g. And I'll write both these out. X plus 4 over 2, or x over 2 plus 2, whatever makes you happy. And so I want to now graph this. I have a few options. One option is just to look at these equations, and probably this one, because that's a linear function with a slope of 1/2, or a gradient of 1/2, and a y-intercept of 2. And I can just plot that. And so I find the y-intercept of 2, so that's right here. The gradient is 1/2, so up 1 over 2, up 1 over 2, and I got my line, which I'll just grab a ruler for and draw. However, another perfectly valid way of doing this, which in some ways you may find better. Let me label this. So this is the inverse of g. is to go back to one of the fundamental ideas of inverses, which is that our inputs and outputs are swapped around, or in terms of a graph, our x and y's are swapped around. So if I just look at my graph of g of x, which I'll label right here, the one in red. If I just pick a point, maybe I'll look at this point right here. That point is at 2, 0. I put in a 2, I get out a 0. I know the opposite must be true for my inverse. For my inverse, if I put in a 0, I must get out a 2, which on a graph means my x and y's are swapped around, which leads me to this point right here. This 0, 2. Notice the 2 points kind of complement each other. And if I want to visualize a line, I just need one more point. Maybe I'll look at this point down here. I'll draw this in red. And so this point down here, if I look at the coordinates, is 0, -4. That means if I put in a 0, I get out a -4. For the inverse, it must be the other way around. I put in a -4 and I get out a 0, which leads me to this point right here. And I can see how visually these two graphs are related to one another. Now, these two graphs are actually reflections of one another, but it's a reflection on this diagonal line of y equals x. For example, the line of y equals x, I'm going to draw in orange here. It's all the points where x and y are the exact same. And if I draw that, sort of a dashed line here, perhaps you can see that that line is actually a reflection line. Everything on one side of the reflection line reflects to the other. It's a reflection line at an angle, so it's not as obvious as a perfectly vertical or perfectly horizontal reflection. But this line of y equals x is the reflection line between these two. And anytime you're dealing with inverses, you can always imagine them being reflected on this line. Although, in terms of visualizing it in detail, you're probably better off just doing what I did, which is find a point, think of its coordinates, and realize the inverse must be that all swapped around. Which makes sense. Algebraically, we're swapping around our x and y's. In terms of functions, we're swapping around what goes in and what goes out. Which leads me to domain and range. One of the key ideas of inverses is that the domain and range of an inverse is swapped around from the regular function, or the other way around. If you know the domain and range of a function, you just swap those around, and that's the domain and range of your inverse. So how can I use that for this? I have h of x being 3 over x minus 1. I want to find the equation for the inverse, and then eventually I'll use that to find the range of h. A lot of things to think about. Let's do this one step at a time. First, let's find the equation for h of x. And again, I'm going to take this, I'll write it first as y equals 3 over x minus 1. Swap around my x and y's. So x equals 3 over y minus 1. And solve for y. I have a few options. One option is to, because I want to get y by itself. Right now I have y in the denominator. I could multiply both sides by y minus 1, which will cancel that out. So I have, if I distribute this out as well, I have xy minus x on one side and just 3 on the other. Okay, I'm trying to get y by itself. I can then add x to both sides. I'm almost there. Xy equals 3 plus x. And if I want to get y completely by itself, divide both sides by x, and I get 3 plus x over x. That's one perfectly valid way of doing it. Or, which is faster if this makes sense, if I go back to what I started with here, 3 over x minus 1. Yeah, you may have learned when you're solving equations like this, when you have an expression where you have this fraction equaling a single value here, you can always, what's always equivalent is if you swap these two around. And the reason it works is kind of what I've shown before, but if you've seen that before, you may feel confident just jumping straight to x minus 1 equals 3 over y. Oops, what am I doing? Silly me. First I got to swap around x and y. Forgive me. That said, similar idea. If I swap these two around, that's what I meant to do. First, I got to swap around my inputs and outputs. So I get y minus 1 equals 3 over x. Add 1 to both sides. Y equals 3 over x plus 1. And keep in mind, these two equations are equivalent. For example, if you look at what I have right here, off to the right, if I just find a common denominator and multiply the top and bottom of this by x, you end up what I have over here. So I'll write both down, but either way, I've now answered this question in two different ways. And so I'll just write down the inverse of h is either 3 plus x over x or 3 over x all plus 1. Same thing. So now, there's my inverse, solved two different ways. I want to now use this to determine the range of h of x, not the inverse. So keep in mind, this is the key idea. The range of h of x, our original function, is the same as the domain of the inverse. And so if I can find the domain of my inverse, which is right here, then I know the answer to the question. And so let's just look at this. What's the domain of this? And while I could graph, I could graph any of these and see it, I'm hoping we can realize the domain fairly quickly by realizing that if I look at these equations, with either one, x cannot be 0. If x is 0, I'm dividing by 0. And remember, division by 0 doesn't make sense. It's undefined. And so any other number is okay. And it's a little more obvious if you look right here. Aside from you can't divide by 0, any other number can go in there. Because again, if you look at this equation right here, it's 3 divided by a number of your choice, except 0, and then add 1. Besides 0, you can divide 3 by anything you want. You can add 1 to anything you want. So x can be any number you want except 0. And so therefore, the domain of the inverse is x can be any number but 0. Other than that, x can be any real number. Any real number as long as it's not 0. Which means, therefore, I've answered the question. The range of h of x is the same thing, except the range is in terms of y. So y can be anything but 0. Other than that, it can be any real number. And there's other notation you could use as well.